Hey everyone, it's Brock here, and today I'll be talking about NOIST, which stands for Non-Interactive Single-Round Threshold Signatures. So NOIST is a new TFN threshold signature scheme I've discovered myself. Here's a bit of a competitor breakdown. If you're familiar with Frost and Rust, it differs a lot further. So in terms of like interactivity, I guess that's the main thing here. NOIST, let's start with the rounds first, right? NOIST guarantees to produce a signature in single round versus Frost and Roast. Well, Roast is a wrapper around Frost, so the idea in Frost is effectively the problem there. I would say is a disruptive signer it forces the redo of the entire round. So the idea there is you reattempt round until it succeeds. Like you do round again and again and again, it succeeds. Like until the round yields a valid signature. Rust does it's the same, but it does in parallel instead of one by one. So it's kind of like sessions one by one versus sessions in parallel thing. Versus NOIST, well, it's guaranteed to produce a signature in a single round. So all you do is running a single round with a pre-processing. If you have done the pre-processing, then you're good to go. You just do some partial signature and aggregate them all, and you're good to go. And in terms of non-interactivity, well, so what does non-interactive thing stands for? Well, in Frost and Roast, whenever you are to sign a message to participate in a session, you need to ideally, you need to run a server, right? You need to run the signatory, the protocol on an uptime software instance. Simply because again, a disruptive signature forces redo of the entire round, so it's a time critical setup in a sense. Versus NOIST, because it's guaranteed to produce a signature in single round. If it's run in non-interactive setup, because you can opt into interactivity if you want, because that way you get signature in constant time, which is great. But you might as well opt out and say, okay, I don't want to run a server, and simply I want to sign, say, from web interface or smartphone or whatever, anytime and anywhere, if timing is not a concern, right? If timing isn't a concern, but if you want somehow be able to produce signatures still, for a jointly controlled group key of some sort, sometime, anytime, anywhere, it's guaranteed that your partial signature is going to yield, when combined with others, a valid full signature. So it works, at least it works well in that setup. Like you can non-interactively produce a signature, versus Rust has no such ability. And when NOIST is run in an interactive setup, you produce a full signature in constant time. Of course, you could do that as well in Frozen Rose on the optimistic case, assuming no disruptive signers there. Well, you got O1 too, but of course, when we talk in terms of the cryptography protocol, when we talk about cryptography protocols, we think in terms of the adversarial scenarios, and in Frost and Rose, the problem there is, again, if you at least T signers, at least T participants, good actors, and a one or more disruptive signer from a subset of n minus T, then the larger the set is, the signer group is, the more time non-optimistically it takes to produce a signature. Rose does a bit of a better job, right? Because it runs sessions in parallel, so it's kind of more of a log-n thing, the end, if I'm not mistaken. But still, NOIST is O1. Simply you compute a partial signature and aggregate them all in, while you end up with a valid signature. in constant time when it's run in the interactive mode. And in terms of mutability, well, frozen rules are like set in stone, like the quorums. I'm talking about the signatories, the quorum. When they distribute the shares, when the shares are distributed, the quorum is set in stone. I mean, Frost as it's described, right? Ross as it's described. It's set in stone. It's immutable. Versus NOIST, you can add, remove members, or even change the setup parameters such as the threshold value. And that leaves the group key unchanged. So you can redistribute the shares and still you get the same group key. So that's a cool sort of primitive. So Frost, so NOIST has 3 phases or stages. So in the setup phase, you run the DKG protocol. So you get a group key and shares associated with the group key, and agree on the encryption keys. This is important, right? NOIST relies on an encryption mechanism we call VSE, Verifiable Secret Encryption. It's a new primitive used in NOIST. Unlike Frost and Ross has no like encryption of any kind, and we do. We'll come to that, of course, later. And in the pre-processing phase, we create the nonces, a pool of nonces. This is kind of similar to Frost, but it's different. In pre-processing, we create or stockpile a pool of nonces, a bunch of nonces, kind of like stacking nonces. And the two can be combined. We can combine setup and pre-processing in one. And then that leaves us signing. So if you've done the setup and pre-processing, and that translates to having the group key, the shares, a pool of nonces and shares associated with these nonces, well, it's pretty straightforward to sign a message. Simply, you create a signature. Of course, you agree on the message and create a partial signature and aggregate them, like whether you have a central coordinator or not, right? Simply aggregate the signatures in one, then you get a full signature, simply in constant time, if it's interactive, or otherwise in a single round anyway. So the idea is we use an encryption of some kind. It's a pretty easy, like pretty like reasonable. Like it's a pretty straightforward primitive to reason about. I'll come to that, but I'm using encryption to during the DKG process, and we and initially, and to do so we need to agree on the encryption keys, and we do that at the setup phase, right? We agree on the encrypt. It's kind of like one way, like it's kind of like symmetric encryption of some sort. We're encrypting the secret data, but we need to agree on the encryption keys first, and that's what we do at the setup phase. The idea also is to use DKG not only for key gen, like not only to create the group key, but also to create nonces. So that's sort of mainly how NOIST differs from the others. We create pool of nonces at pre-processing, and encrypt nonces. I mean the secret nonces, the secret values, the scalars, in a way that can be verified by anyone. So anyone sort of, it's kind of like a zero knowledge proof of knowledge kind of thing. Anyone can verify the authenticity of the encrypted data, which is a scalar. It's some integer group, like a modulo group order, right? But you can but anyone can verify that the encrypted data is not something garbage, right? It's something it's something it's some desired data, right? But the data can be decrypted only by one guy, well, one party, right? The desired entity can decrypt the data, but anyone can verify the authenticity. And when we sign the message in the partial signature, we add the Lagrange coefficient. Not only typically in Frost we add that to the private secret share of the group key. Here we not only add that to the group key secret share, but also to the private nodes, the secret node share, and the partial signature. So the basics, well, if you're familiar with Frost, you've got this S. This is a scalar full secret. The T is the number of shares the that you need to hit, and N the number of total shares. You run the polynomial, right, with the constant term being S, and with a bunch of polynomials, and the degree being T minus 1. F0 is the full secret, and E, the tuple E and FE is the ETH secret. From the it's a polynomial evaluation, and the Lagrange is from if you're familiar with Frost, it's the Lagrange the interpolating value, right? It's basically the product of all signer indexes divided multiplied by the multiplicative inverse of each individual gap, except for E. So NOIST relies, NOIST is based on 3 primitives. So distributed key generation is nothing new, used in Frost, ROS, as well in NOIST. VSS, verifiable secret sharing, it's simply primitive, right? Using Frost, ROS here as well. VSC is how NOIST largely differs from the other two. It stands for verifiable secret encryption. And this is what this whole encryption stuff is all about, I've been mentioning. So distributed key gen, right? So effectively we run a polynomial, and the hiding point, we run 2 polynomials, the hiding polynomial and the binding polynomial, right? So the constant term of the hiding polynomial times G is our hiding point, and simply the constant term of the binding polynomial, the scalar SB times G, is our binding point, with the polynomial degree being T minus 1, the constant term, and the variables. And the hiding group point, well, when we sum all points, the points, the first, the constant term times G, and we sum it all, and that gives us the hiding group point. And if we do the same for the bindings, the constant term of the binding polynomial times G of all participants, if we sum it all, that gives us the binding group point, the pre-point. The binding value for E, and this is mainly for the Rojki attacks, to avoid the Rojki attacks, sort of like two nonce combined later, combining the 2 nonces. So it's a hash, it's a constant, it's a scalar, it's a constant value, it's a scalar, well-known scalar value. It's a hash of the bytes E, the ETH for signer E, like say for the first, second, third, nth signer E. Bytes E concatenated by the hiding group point, concatenated by the binding pre-group point. And if you hash it, that gives you the well-known binding value. And if you add a binding value to the binding group pre-point sum, that gives you the ultimate binding group point. And if you add the hiding group point with the binding group point, the final binding group point, that gives you the full group point. And so in the EKG setup, so we've got Alice, Bob, and Carol. So Alice creates, like this is the DKG setup I'm describing, and we use DKG for both keygen and nonce gen. So it's a generic protocol, right? And so when we run DKG, say we've got 3 participants, to keep things simple, Alice, Bob, and Carol. And Alice creates her own package. And as you can see, it has like this package has VSS bindings, VSS hidings, bindings, VSC hidings, and VSC bindings. So um, so the VSS, as you remember, stands for verifiable secret sharing, and it is a vector of points. It's a vector of t points. And as for the VSC hidings, the VSC, it's two vectors. The first vector it's a vector of n points, and another vector of n scalars. And Alice does the same for bindings. It's just another polynomial. So effectively, the VSS hidings or bindings are the vector of points, and these points are the p1, the first point being the constant term times g, and the other points are the rest of the polynomial constants, the random values times g. The VSS, the VSC vectors, however, these are the secret shares encrypted in an encrypted manner, the secret shares, and the secret shares, the points that the secret shares map to, correspond to. So Alice creates her own package or her own contribution. Bob does the same, right? It creates a vector of hidings, vector of bindings, and hidings, and VSC, VSS. And Carol does the same, right? Creates her own contribution. And then Alice sends her package to Bob and Carol. Bob sends his contribution to Alice and Carol. And Carol sends her package to Bob and Alice. So when we all exchange our value, the package, the contributions, whatever, then we're all set actually. The setup is pretty much over. The sum of the first points gives us the aggregate group key. Effectively, because that's a constant term in the polynomial times g, and sum it all with others, then it gives you the group key. And then the first point in the VSC vector, right? That's the aggregate public share of the first participant, which in this case is Alice. That's Alice. That's her aggregate public share. And the second, the sum of the second points in the VSC vectors, in the first vector, the bindings and hidings, that gives you the Bob's public share, the public share of the second participant. And and here is the third, is 3, right? It's say this is a 2 of 3 setup, and n being 3, the nth, the third point of the vector, the sum of the third point of all VSC vectors is the aggregate public share of Carol. And as for the second vector of the VSC, hidings and bindings, that gives us the aggregate secret share of the first participant, which is in this case is Alice, upon decryption. So the sum of the S1s, it's not, because it's public, it's outright bare, right? It's there, it's known by everyone, it's well known. All packages are well known, right? So is the S values. So the S1, S2, and Sn, these are public values, but they're encrypted, so that only Alice, the intended participant, can decrypt them, but in a way that it's verifiable. But the sum of S1s are effectively the encrypted secret share of Alice. And similarly, sum of all S2s are the encrypted public, the secret share sorry, of the second participant, which in this case is Bob, and some of SN's or is I mean or encrypted secret share of Carol. And so from, in this case, Alice, it's Alice's contribution here, and the P1, from the VSC hidings in this case, it's Alice's is her own contribution. It's something Alice herself contributed, and computed and contributed. Is a public it's a public share, right? It's some public contribution, and it's the public. It's effectively a secret share times G, and you can verify whether this point P1, the public contribution, is it passes the verification against the VSS hidings, simply running VSS verify function. It's nothing new of a primitive. Again, VSS is there for frost and rost. Effectively, we can run VSS verify, and we'll come to that later. But to make sure the P1, the VSC P1 is valid against VSS points. Similarly, we can run VSS verify to make sure P2 VSC is valid against VSS points. Similarly, PN. We do the same for bindings. We make sure P1, the VSC P1, the binding point, is valid against the binding points, the VSS binding points. Similarly, we make sure the P2 VSC binding point is valid against the VSS binding points. And similarly for PN, we do this for everyone, and everyone does it for everyone. So everyone does it's a local verification of some sort. All participants do the same for all participants. All participants run verification for all participants. We do the same for Bob, really. P1, P2, PN for Carol, and bindings and hidings, and when this passes, then we got another layer of verification here. And in this case, we know the P1 is a valid point against the VSS points. We know that P1 is valid. We also need to make sure the S1 is a valid scalar. It's a valid scalar. It's a correct value and it corresponds to the P1. It's a valid scalar against the point P1. And anyone can do it. Anyone can do it. So S1 again is an encrypted value, and when decrypted, it becomes the actual secret value, right? And that secret value then corresponds to the public point P1, the public share. And anyone can verify it though. Like anyone can verify S1 when decrypted maps to P1. But only Alice, in this case the first participant Alice, can decrypt it. So it's some scalar encrypted in a way only Alice can decrypt. But anyone can verify that it's valid. It's not some garbage data. And similarly, S2 is valid. It's a valid scalar against P2, and it can only be decrypted by the second participant, in this case Bob. And Sn, in this case S3, it's a scalar encrypted. Only Carol can decrypt, but anyone, Bob, Alice, Carol, can verify it. We do the same for bindings. It's the same of hidings. And Bob, similar, right? Now it's Bob's contribution. We're talking about Bob created these values and contributions S1, 2, 3, n, right? And anyone in this case, S1 in this case belongs to Alice, right? So Alice can decrypt, only Alice can decrypt S1. Well, Bob can decrypt it too, right? Because Bob computed it in the first place, but Carol cannot compute it. Like, cannot decrypt it. Only Alice and Bob can do it. And S2 here, it's Bob. It's created by Bob, and it belongs to Bob. Sn, well, it's for Carol, and only Carol can decrypt, but anyone can verify it. Same for bindings. It's the same thing, really. And Carol is the same thing. S1, only Alice can decrypt, but it maps to P1. Anyone can verify it. S2 belongs to Bob, and only Bob can decrypt S2. And when decrypted, it gives Bob his secret share. But anyone can verify it. It maps to P1, PP2. And similarly, Sn, same for bindings. So the VSS is a simple primitive, right? So typically in Frost and Rost, we have, when we get a secret share, we multiply it with G and make sure we evaluate the polynomial in a public manner, right? The P1 being the constant term times G, but now it's public to us because these values come from the hidings, the VSS hidings and bindings. So the VSS, the first point of the VSS, in this case here, right, the first point of the VSS plus the second point of VSS times E up until the last point PT, because if you remember, VSS has T points, not N, up until point T times E times T. Effectively, we are evaluating the polynomial in a public manner so to verify the authenticity of point E, and the point E is from the VSC, right? So we are verifying a VSC point, VSC points from here, one by one, P1, P2, Pn, the VSC point PE against the VSS points. So this is effectively the idea. This is the idea. So as for VSC, VSC stands for verifiable secret encryption, and that's again used for decrypting, or encrypting and decrypting a secret share in a way that is verifiable. So let's forget about Charlie for a moment to keep things simple. We got Alice and Bob. So in the setup phase, this is the setup phase I'm talking about. So in order for VSC to work, it's an encryption. It's a very simple encryption primitive. And in order to encrypt, we need to agree on encryption keys first. And this is what I'm talking about. We need to agree on encryption keys. And simply, we're using Diffie-Hellman to effectively encrypt data. So it's a simple primitive, really. You got Alice's secret, and this is her master secret, really, times Bob's public key. That gives us the private point, the secret point, the secret shared point. And if we take the x bytes of this point as our secret times G, that gives us our shared public point. And Bob runs the same thing, right? Bob takes his master secret and multiplied by Alice. Her public point gives us the same secret point, and if we take x bytes as a secret scalar times G, that gives us the public shared point. And if the 2 points are equal, sort of it effectively means Bob has acknowledged Alice's point, the encryption point. Alternatively, we could as well use zero knowledge proof of some sort um, to achieve the same result, right? Alice simply can say, along with the proof case, say, okay, hey, this point is our encryption point. Right? It results from the Diffie-Hellman. Can prove it, but this is a lot simpler to reason about. Simply two parties acknowledge and say, okay, this is our point. Simply acknowledging, let it be, and it is, or encryption point, which is later used for encrypting the secret values, the secret scalars. And so in the pre-processing phase, when we run the DKG protocol, then OS creates a polynomial, random, with random constant value and variables, and creates the shares, evaluates the polynomial to create the shares for herself and for Bob and others, takes Bob's share simply and adds the private X bytes, the private point bytes, to effectively to yield the encrypted scalar, the encrypted value for Bob. And similarly, when Bob's runs the DKG protocol, whether it's for creating group key or creating a nonce, again, it's generic setup, runs a polynomial, evaluates it, and takes her secret, adds the shared secret value to encrypt it, and that gives us the public encryption, the encrypted data, which can then be shared. And verifying this is pretty straightforward, right? SE is public, PE is public. They come from the DKG protocol, and it's public, it's exposed to everyone. This is the encrypted data, right, from the VSC vector, from the VSC scalars vector. Remember the second vector, the VSC, times G of it equals to the public point, the VSC from the first vector, added by the encryption point. The encryption point comes from the setup phase, like from the first place, like it's computed in the first place at the setup phase. It's well known. And these two, PE and SE, comes from the DKG setup from the data exchange. And simply we can run this to make sure the authenticity, whether SE is a valid encrypted scalar against PE, the public share. And simply to decrypt, we take the public private share, the private share which is public encrypted, subtracted by the private share, the private shared secrets, the private encryption secret. The signing is pretty straightforward, right? When you have the shares for nonces and a group key, it's pretty straightforward to sign messages. So for E, a signer from set 1 to n, the Lagrange is pretty straightforward, right? And the binding value, again, from the earlier, it's pretty straightforward. It's well-known. It's a well-known value. So for message M being the kth historical signing attempt, so for each signing attempt, to avoid nonce reuse from the pool, we gotta pick up a new nonce, right? And we do it on a one-by-one basis. And we first compute the challenge E. We pick the nonce from the pool, a fresh nonce from the pool. If there's a shortage of nonce as well, we gotta rerun the pre-processing, which could be non-interactive or interactive. And we picked the nonce, as you can see, before ever like joining the like when you join a signing round in a signing session, then you know in advance what's the nonce gonna be, right? What's the challenge is gonna be, because you pick your nonce from a predetermined set of nonces from pool of nonces you've created in pre-processing, and it's pretty straightforward to sign. Like it's pretty straightforward to go from there. The group point is known way earlier, right from the setup. Uh, the group nonce is known from pre-processing. Simply pick the group nonce from the pool, the message, and hash it with the tag hash, and gives you the challenge E scalar. And so to compute the partial signature, you get your hiding secret share. This is the nonce, right? This is you pick this from, just like how you pick your public group nonce from the pool. You pick your secret nonce from the pool as well. It's results from, again, the DKG protocol, and by summing your own secret shares of all participants, it gives you the aggregate hiding secret nonce multiplied by the Lagrange, and this is how mainly NOIST differs from other protocols, added by the binding secret nonce share multiplied by the binding value multiplied by the Lagrange plus challenge E times the, similar to nonces or the private nonces here, I add my own secret share, the secret group share, the hiding share, plus the binding secret times the binding value times Lagrange, and this is effectively how signing is done, right? It's handled, when you and simply to verify it, and this could be done by a central coordinator or whatever really. To verify it, we take the partial signature SE, the scalar, times G, and if it's equal to the hiding public nonce of the participant times the Lagrange, the interpolating value, plus the binding public share of the participant, times the binding value times the Lagrange, plus the challenge E times it's the partial group point of the hiding point, and the partial binding group point times the binding value times Lagrange. If it equals again to the SE from the participant times G, it passes the verification, and when it passes, it's pretty straightforward to sum it all. Simply we add partial signatures who pass, and if you have T numbers of them, it gives you a valid full signature. As for resizing, NOIST, it's a mutable, dynamic, flexible design, really. It's a flexible community design. It's a flexible design. You can add remove members and change parameters, kick off members and such, in a way that leaves the group key unchanged. So you can effectively say jointly control npubs that way, or even Bitcoin addresses, without, again, taking an on-chain action, so to speak. So remember from earlier, we run two polynomials, hiding polynomial and the binding polynomial, with the constant terms, the degree being t-1, and then we run the DKG protocol, sum the secret shares. When we sum it all, that gives us my own partial secret share. And to create a new polynomial, say to kick out a member or add a new member, we create a new polynomial the constant term being my my hiding aggregate share, secret share, time plus my binding pre-aggregate secret share times the binding value times the Lagrange with the rest of the polynomial. So I pick new random values. So and a t is a new value, right? You can resize t as well. You can change the threshold parameters. So effectively, you create a new polynomial with new random variables and the new t value, but the constant term is not random. It's derived from the earlier setup. Because this effectively, in the parentheses, this is my partial share, the partial secret share of the group key, of the full key, right? And effectively, if you add enough number of these together, because it has the interpolating value here. If you add enough number of these, in theory, it gives us, as in a regular Shamir secret sharing setting, it gives us the full the secret, the group secret, the group secret, which is unknown, which is not known to any party. And if the idea is to create points from this new polynomial, just like what we did before, just like what we did with the regular the hiding and binding polynomials, right? We create a point, a vector of points, the VSS points, the VSC points, and the scalars out of this new polynomial. The new random, the fresh random values are for the variables, and the constant term being from derived from, again, the earlier setup, in a way that leaves the group key unchanged. And from the new polynomial, we can partially verify it. So the point 1, the P1 from the VSS, it's a bunch of points from the VS. So VSS from a bunch of points from 1 to t. For every single one of these, simply we the hiding aggregate point of the eth signer plus the binding aggregate point of the eth signer times the binding value times the interpolating value. If it's equal to P1, because the P1 is, again, the constant term of this new polynomial times G, and if it's equal, well, to the public hiding aggregate of the secret, the group secret, and the binding aggregate, pre-aggregate secret of the group times B times Lagrange, then anyone can verify that this new polynomial is valid. You also need to verify the VSS points and the VSC points, just like what we did before, to make sure that it's all valid, the whole thing is valid. And so, say we got Alice, Bob, and Carol. We want to kick out Carol from our federation or quorum or whatever, and now we want to add Eve instead. Then what happens is Alice creates her new package. In this case, we don't have bindings or hidings. We only have one polynomial. So we got a vector of t points and two vectors, a vector of n points and then a vector of n scalars. Same goes for Bob. Bob creates his own contribution. And so to create a new secret share, we redistribute the shares to Alice, the S1 from Alice, her own contribution, and S1 from Bob's. When decrypted and added together, that gives Alice her new secret partial secret share of the group key. Similarly, S2 from Alice and S2 from Bob himself, when decrypted and added together, gives Bob his new partial group secret share. Similarly, for Eve being the third participant, S and S3, S third, S3 from Alice and S3 from Bob, when decrypted and added together, gives Eve her secret share of the group key. So that's pretty much how it is, how the protocol works, like overall. And in terms of the use cases, so rollup, it's a Bitcoin, for those who are not familiar, it's a Bitcoin payments rollup. It's kind of like a timeout tree with virtual channels. And it's a very performance critical and time critical design, and so that's where I think NOIST fits really well. Because you can run NOIST in an interactive setting, and produce partial valid full signature in constant time. And the T of N in a very, very large setting really could be really thousands of tens of thousands really, because you get a signature in constant time. So as for ORIC, you can form very, very large ASB federations, like similar to Rollup, aggregate liquidity, jointly controlled shared UTXOs and connector outputs. BitLock is another project I've been working on. Due to the non-interactive properties of NOIST, you can jointly control npubs as well as Bitcoin addresses. Alright guys, thanks for listening. Happy to help. If you have any questions, like feel free to reach me out. I'm working on an implementation. I guess that should be out in a few weeks, but in the meantime, yeah, feel free to reach out.